Okay, so I want to go ahead and talk about how to graph the first and second derivative given this original function. Okay, so we're going to say that this is my original function up top, and we're going to use that original function to graph the first derivative and the second derivative. Now, when I'm thinking of graphing the first derivative, really you have to understand what the first derivative is. It's just instantaneous rate of change or slope. Right? So I'm using the slope of the original function in order to graph the derivative. Or in other words, I'm going to be looking for where the original function is increasing and decreasing, okay, in order to graph the first derivative. Here's what I like to start with. I like to start just by identifying where my maximums and minimums are. Because what is the slope at each maximum or minimum? What is the slope there? You can just call it out. What's the slope at a maximum or minimum? 0. Okay, so that's an easy point to plot on the first derivative graph. I'm going to make sure that the maximums and minimums of my original function line up with the x-intercepts of my first derivative. Okay, so that gives us a good starting point. And now I'm looking at where the original function is increasing or decreasing. So right here, we're just working from left to right. My original function would be decreasing, right? So should I graph the first derivative above the axis or below the axis? That would be below, right? If it's decreasing, I'm going to graph it below. Okay, then I move on to the next spot. Right here, I'm actually not going to use blue because that's kind of hard to see. Let's go ahead and use green. In the next spot, it's increasing. Do you see that? So for the first derivative, would I graph it above or below the axis? Above. Okay, and eventually it's going to have to return to that x-intercept. Okay, but it's graphed above the x-axis because those slopes are positive values. Okay, then I go back up here, and then finally we end up where it's decreasing now. So again, I'm going to graph it below the axis. Does that make sense? And I'm not surprised that I ended up with a parabola, because my original function up here has a shape like a cubic function, right? It's some kind of cubic function, some type of degree 3 function, which if I take the derivative of a degree 3 function, right, 1 degree less would be something squared, right? So it makes sense. And also notice it's decreasing from left to right. So if I'm thinking of some kind of cubic function that's decreasing, when I take the derivative of that, you can see how you get a parabola that opens down. So that's making sense. All right, now I'm going to go back to the second derivative and use the original function to graph the second derivative. How is the second derivative related to the original function? That has to do with the concavity of the original function, whether the original function is concave up or concave down. Remember, when we're doing the concavity test, we're using the second derivative quite a bit. Okay. So looking at this original function, I can see that this side is concave up until we get to about this point right here, right? And then my function changes to where now it's concave down. So wherever the concavity changes, in this case, the concavity changes right here at this point in the middle, that's where my intercept is going to be for the second derivative function. Okay, so if I'm going to the second derivative function, I'm going to make sure that my intercept is right here. Right, it lines up with the point of inflection from the original function. Where my original function was concave up, should I graph the second derivative above or below the axis? If it's concave up, then I'm going to graph the second derivative above the axis. And where my original function was concave down, should it go above or below the axis? It should go below the axis. Okay, right? The original function was concave up, then we hit the point of inflection, and then it was concave down. So we had above the axis, we have our x-intercept, and we have below the axis. Again, I'm not surprised that the second derivative is linear, right? If this first derivative is a parabola, if I go 1 degree less, then shouldn't I get a line? okay, with some kind of positive or negative slope. It's negative slope in this case because my parabola was opening down. So when I graph the derivative, I got a line with a negative slope. Does that make sense? Another way you could do it, rather than relating it to the concavity of the original function, you could just use your first derivative graph to help you. You could think to yourself, okay, well, let's imagine that this is the original function now, and this is one, like the first derivative. Like we're just relating the first derivative and second derivative together, and we're using the slopes of the first derivative to help us graph the second derivative. So you can see if I'm doing it that way, here it would be increasing. Oops. Here it would be increasing. So I graphed it above the axis, right? I get to my maximum or minimum point, which lines up with my intercept, right? And then here it's decreasing, so we graphed it below the axis. Okay, so if you want to just use the slope of the first derivative to graph the second derivative, that's another way to do it. I don't care how you get your graph of your second derivative, as long as it's right. You can either relate it directly back to the original function and look at the concavity of the original function, or you can look at the slopes of the first derivative to help you graph the second derivative. Okay. Any questions about that? Okay, that's all.